Okay, I'm very pleased to introduce Lars Kristiansen, who will speak on the first-order concatenation theory versus first-order number theory.
Thank you very much. Thank you for inviting me. I'm so happy to be here. And my talk will be on something that I believe you know very well. First-order number theory. Here is the language of Peano Arithmetic, Robinson Arithmetic. And here is the language of first-order bit theory. You see we have three constant symbols, and we have a binary function symbol, and that's all. So, and we have standard modes. The standard model for Peano Arithmetic we know very well. It's a model where the universe is the set of natural numbers, and these operators works the way you would expect. The standard model for bit theory, or I should say concatenation theory, that's the unestablished term, but I say bit theory because the universe is the set of all finite bit strings, and this constant denotes the empty string, and this constant denotes the string that contains one and only one bit, and that's the 0 bit. And this constant denotes the string that contains one and only one bit, and that's the 1 bit. And this is concatenation of strings. So I use B to denote this standard model, and N is the model for number theory. Now this language seems very meager, and you might think, it's not a very expressive language. That's what you first think, or at least that's what I first thought. But after thinking for half an hour, you realize that the language is indeed very expressive. It's not hard to prove this theorem. A theorem that says that for any functions from the natural numbers into the natural numbers, we have a formula with this property. So we can define any computable function in the standard model for the theory, and thus is undecidable if a formula is true in the standard model. Now, it's of course also undecidable if a formula of number theory is true in the standard model. It's even undecidable if a formula of this form is true in the standard model. That's the negative solution of Hilbert's 10th problem. Now, on the other hand, Hilbert's 10th problem have a positive solution in bit theory. It is decidable in bit theory if a formula of this form is true in the standard model. That's proved by this guy. So a very natural question then is, for which subclasses of bit formulas can we or can we not decide truth in the standard model? So to answer this question, we will introduce bounded quantifiers, similar to those we know from number theory. And so what we do is to extend the language of bit theory with a binary relation symbol, and then introduce the bounded quantifiers like we do in number theory. And then we can define the sigma formulas inductively. A sigma formula is a formula that contains no unbounded universal quantifiers, and where all the negation signs are next to atoms. So also known as sigma 1 formulas or sigma 0, 1 formulas.
What is the Oh, okay.
Yeah, no, please ask question.
I just see the answers on the next slide.
You see the answers on the next slide, yeah? So, yeah, so we have a very good question, yes. How do we interpret this symbol in standard? So it turns out that we have a number of options now. In contrast to in number theory, we only have. So we might interpret this as x is a substring of y. We might interpret it as x is a prefix of y. There are other options, like number 3, x precedes y in a lexicographical ordering, and there will obviously also be more options. So far we have investigated option 1 and option 2. So now, from now on, B, the standard model, where this interpretation is the substring relation, and D denotes the standard model where this relation is the prefix relation. And to make life a little bit easier, I will from now on use this symbol in place of this symbol when we are working in a model where this should be the prefix order. So you should read this as U is a substring of V, and this as U is a prefix of V. And we have found sigma complete axiomatizations of both these two models. So one of our axioms should come up now. Yes. So you see the first 4 axioms deal with concatenations, and then we need 6 axioms for dealing with the substring relation. The prefix relation is easier to axiomatize. You only need 3 axioms. And this 4 is the same as for B. So this is the theory, first order theory B, and this is the first order theory D, and both of them are sigma complete. We can prove any true sigma sentence from these axioms. And we can also prove that make a stronger theorem on the finability of computable functions. We can prove that for any computable function there is a formula, a sigma formula that defines the function in the standard model. That's true for B, and that's also true for D. It's harder to prove for D, but altogether it's very, very hard to prove these two theorems. So, what's the situation now? Well, it's undecidable if a sigma sentence is true in the standard model B and the standard model D, because we can represent all computable functions in these models. But due to this result of mechanism, it's decidable if a sentence of this form is true in the standard models. So, can we say anything more about the border between the decidable and the undecidable? And what we have to do then is to start to count quantifiers in sigma formulas. So, a sigma formula phi is a sigma NMK formula if it contains n unbounded existential quantifiers, m bounded existential quantifiers, and k bounded universal quantifiers. So n unbounded quantifiers, bounded existential and bounded universal quantifiers. And then I call it a fragment. This fragment is the set of MMK sentences that is true in the standard model.
So is it the demand that unbounded ones are all in front?
The unbounded ones, yes, the unbounded ones are in front, and the existential ones, and then there are bounded existential ones, and then finally. Yes, but it's important to remember.
Well,
I tried to come up with some good notation, but I haven't come up with anything better than that.
in arithmetic there's a lot of confusion about that because the equivalence in strong series of these things.
So it's in pre-next form, yeah?
Yeah.
It's in this order.
No. No. We will return it. That is also a good question. We return. No. The sigma formula is not in pre-next form.
Okay.
It's, you have the negation sign next to the atoms, but that's all.
Okay.
That's all. Yes, and this is the fragment where with respect to the structure D. So, some decidable fragments. These fragments are decidable. And that follows from the fact that we have complete axiomatization, so the sigma complete axiomatization. You can of course also check by brute force if a formula without unbounded quantifiers is true. Now, to identify more decidable fragments, we have proved two normal form theorems. So, I have to introduce some notation again. This denotes one of the quantifiers that may appear in a sigma formula. So, if this denotes an unbounded quantifier, this term T is just irrelevant. Alright, here is a normal form theorem for the structure D. Any sigma formula is equivalent in D to a formula of this form. So you see, what's surprising is that the matrix can be reduced just to a single equation. We have actually not done all the work here on our own. We use a lot of lemmas from work of Vichy that we found in the literature. So, well, you see here we have the quantifiers.
Is that provable in the theory?
No. I need more axioms to prove that. So I always not talk about we are using in the standard models. And you see, so you have a pre-mixed form here, but we don't have any control over how the quantifiers automate. There might be bounded quantifiers outside unbounded ones. There might be. But if this phi does not contain bounded universal quantifier, this normal form will not contain bounded quantifiers at all. So then we call mechanics theorem is decidable if a formula of this form is true in D, and by our normal form theorem we can take any formula in this fragment is equivalent indeed to a formula of this form, and thus this fragment is decidable for all. We have also a normal form theorem for B. And now you see in B any formula is equivalent to a formula where you only have one unbounded existential quantifier. And you can have it in the front, and these will be bounded ones. And again, you can reduce the matrix to a single equation. But do now observe that it does not follow from this normal form theorem that any formula in this fragment is equivalent to a formula of this form. It does not follow. So we cannot use Machanic's result to conclude that this fragment is decidable, and this is a non-trivial open problem. And where do we find the roots of this problem? Well, we are able to prove that a formula of this form is equivalent in the model to a formula of this form. We are not able to prove that it's equivalent to a formula with only existential quantifiers. So, when we transform a sigma formula containing this formula to its normal form, we have to introduce new bounded universal quantifiers. So that's why we have this other problem. So, decidable fragments. And to identify decidable fragments, undecidable fragments, we use post-correspondence problem. You see, this is the problem. The input to the problem is a finite list of pair of bit strings. And a solution is to find a non-empty sequence of indices such that you have this equality. So you have a puzzle. This guy and this guy should be taken from the same pair. And the next guy and the next guy should be taken from the same pair. And you have a puzzle, and you should try to make the two strings equal. And this problem is undecidable. So, and of course, this problem, we were very happy when we found this problem, because this problem is very suitable to express in bit theory. So, this fragment is undecidable. And the proof is that we, from an instance of post-correspondence problem, can compute a formula, sigma 3 0 2 formula, such that this formula is true in the standard structure if and only if this instance has a solution. We do the same for this fragment, 4 1 1. Proof by the same recipe. This fragment, now we are in B. It's undecidable, this fragment is B1, 2. So here's a summary of our results. Decidable, undecidable. So you see, we are rather tight results here. There are some open problems, you can work them out for yourself. I was confused. I tried to write up the open ones over here, but I got confused, and then and here are the results for the fragments of this side. So, how much time have I used? 10 minutes more, yes. So, I don't have much more. It's, so it's in our way. This research started from scratch. I was making exercises for undergraduate students, and I realized the expressive power of this language of big theory. And it took, like I worked out that it goes back to Tarski and Quine, and then it was sort of long break in the history until Grzegorczyk writes a paper about 10-15 years ago. And after that, there been some work. But this work is it's
Chalk is over there.
Chalk. Yeah. This work is centered around a theory collection of axioms called TC that goes back to Tarski and Grzegorczyk, and all this research seems to be related to the essential undecidability of fragments of TC and interpretability between theories. Our axiommatizations are rather different. And of course, do anyone know TC? Know this research? No, all right, so so I will not talk more about that, but it's a natural way to proceed our research is to see how our axiommatizations relate to this theory of TC. Another reasonable thing to do will be to start to look at induction in this theory, and we can have induction scheme like if something is true for the empty sequence, and if it's true for a string, if that's implied that then it's also true for these two strings. Then it should be true for all strings. Seems like a natural induction scheme. I cannot. So then we can, since this is a complete sigma one theory, you can use it as a base theory, like Robinson Arithmetic, and then we can extend the theory with induction schemes like we do in Peano Arithmetic. But I don't know how fruitful this will be. So if anyone here has anything to say about that.
Yes, so of course, Fernando Ferreira studied this in his PhD thesis. So there's the analogy between Busser's theory, S12, and a string theory, right? And so this has been intensely studied and also independent, I think, of the Quine, etc. line, right?
So that's some work.
Because the point is that strings are a natural way of thinking about p-time computation.
Yes.
Yeah. So there's the Fernando Ferreira line, and there was analogs of S12 were developed for strings, and it's precisely this.
Precisely this. Yes. All right. That's useful to know.
Yeah.
When I started it work, I expected that more of what I showed here should be known, but I have not seen it anywhere. So, right, but fine. If there are not any questions, I'm done.
Well, is he done? Are there questions? Questions?
Maybe more remarks. The business of the mutual interpretability. So it seems as if we have a kind of big cloud of series that are the same modulo mutual interpretability. So adjunctive set theory, PA minus, and TC and all related series, right? So there's a kind of basis, a kind of basic theory that is extremely robust and at least modulo mutual interpretability independent of your representation. Of course, as soon as you want stronger relations of sameness, everything falls apart. But for example, I predict that Busser's theory and Ferreira's theory are synonymous or definitionally equivalent. But nobody ever did the homework to really do this. But I think it's more or less predictable how that should go.
Good question, David?
Can you think of some problem which is definable over the models B or D, but this problem is strictly below the halting set and it's non-trivial in terms of Turing reducibility?
So a problem that is definable in B or D?
Yes, like you can define it over B or D.
Yes.
But you cannot solve the halting problem with that problem, but it's non-trivial. Because you showed us that some fragments are undecidable and so on, but I'm not sure how strongly undecidable they are, and probably you can solve halting problem with these fragments, but
if you can define a problem of low degree or something.
Yes, something like that.
Well, if you can do it in Peano Arithmetic, you can do it here. But then I'm not thinking about that, but you can define here what you can define in Peano Arithmetic. I think it should be the same. You can.
More questions? Okay, thank you very much.